Hello again, Mrs. Thompson here, and today we're covering periodic trends. This is part one, and in part one we're going to go over how to discuss the trends on the periodic table, and then two of the major trends, atomic radius and ionic radius. First, we need to know about periodic law. This just states that when you arrange the elements by increasing atomic number, we start to see several patterns, and those are what we call our trends. Another thing that we start to see is that elements in the same column of the periodic table, which we call families, have very similar chemical and physical properties. Our entire discussion on trends depends on the strength of the nucleus of a particular atom or as you go across the periodic table. And so we need to know two things about the nucleus. One is its nuclear charge. And the nuclear charge just means the total number of protons in the nucleus. So the thing that gives it its strength are the protons because they're positively charged. And they will attract negatively charged electrons. The more protons an atom has, the stronger the nucleus is. Where the number of protons increases the strength of the nucleus, there's something that can actually decrease the strength of the nucleus. And that is all of the layers of electrons that exist around that nucleus. And so here we go. This says the shielding effect is the weakening of the nucleus that occurs when inner electron shells block outer electron shells. The more shells you have, energy levels, we can think about these in terms of Bohr diagrams, the more shielding that's occurring. Okay, so you have to remember that the nucleus has protons, which are positively charged, and they are attracted to electrons, which are negatively charged. Here we have two magnets to show that those opposite charges will attract each other. Okay, shielding works like this. So if I have a layer of electrons, they're going to weaken the pull of the magnets. Okay, if I keep adding more and more shells, I'm weakening the pull. Okay, until I keep adding more and more shells. And now the magnets can no longer feel that attraction and they just fall down. Just like if you were sitting in a SeaWorld show and you were in the splash zone, all of these people that are right here would get really, really wet by the whale splashing water. People behind them, even though the water is reaching past them, they would get less wet because the people in front would shield them from the water. So this is kind of an analogy for the nucleus, okay? And this is the pull of the nucleus to those outer electrons. In order to talk about the trends on the periodic table, we'll look at it two ways. One, across a period, so from left to right within a row, and down a group from top to bottom within a column. So again, let's talk about nuclear charge and how it strengthens the nucleus. And so protons attract electrons. Okay. If you have more protons, that proton will pull on the electron with even more force. They don't actually touch, but just imagine here, the stronger the nucleus by more protons, the stronger the magnet inside of that nucleus for those electrons anyways. All right, so we can think of protons as something that gives our atom strength. So let's discuss the trend in nuclear charge. From top to bottom, the atomic number increases. So the number of protons increase, so the nucleus gets stronger and stronger that way in terms of nuclear charge. And then from left to right, we are also increasing in the atomic number. So the number of protons are increasing and the strength of the nucleus or nuclear charge increases. And next we'll discuss the trend in shielding. So first we need to remember that electrons repel each other. So just like magnets, when you put them on the same end, negative to negative, here's my magnets, if you can see them, they push each other away. They repel. So just like that, here are two electrons pushing each other away because they're both negative. As you go down a group, you gain another energy level, and so you gain another shell. And so as these valence electrons are trying to feel the pull from the nucleus, they're being blocked by all of these inner core electrons. All of these inner core electrons are repelling the outer electron plus each other. And so you have lots and lots of shielding that's occurring. So if you look at this chart, you can see that as you go down a group, you're gaining in the number of shells. So shielding increases down a group on the periodic table. Then from left to right across a period, you can see, let's take this one, the number of shells are constant as you go across. So they're not changing. The number of shells stays the same, so the shielding stays the same. Okay, so combining those two, shielding and nuclear charge, the net effect is this. As we go from left to right, the strength of the nucleus increases. And as we go from top to bottom, the net strength of the nucleus decreases. We'll discuss why in just a moment. But what we end up having is the strongest elements up in the upper right-hand corner of the periodic table, ignoring the noble gases, and then the weakest elements on the bottom left-hand side of the periodic table. So just remember, francium is the weakest, and fluorine is the strongest in terms of the net effect on the nucleus. All right, so which seems to have a greater impact on the strength of the nucleus, the nuclear charge or the shielding effect? Well, if you look at nuclear charge, as we go down a group, this increases in nuclear charge, but the strength of the nucleus is actually decreasing. So that means that shielding is playing a bigger role on the strength of the nucleus, the net effect of that. Okay. Next question, why does francium's nucleus have a weaker pull on its electrons than sodium's, even though francium has more protons to attract those electrons? And the reason for that is all of those shells, which we call a shielding effect, weakens the pull of francium's nucleus. So it says francium's nucleus is weakened by the increase in shells. Our first real trend is atomic radii. First, we need to know how that is measured, and it's measured by taking two atoms, putting them together, and measuring from nucleus to nucleus, and then cutting that distance in half to give you the atomic radius. And basically all that's telling us is how big the atom is. Something that plays a big role in the size of the atom is the pull of the protons in the center of the atom for the electrons on the outside. And so the stronger the pull, the smaller the atom gets because those electrons are being attracted to those protons. So in this picture, we can see the atomic radius increases from top to bottom on a periodic table, and then it decreases from left to right. So let's discuss why. So why does it increase from top to bottom? Well, as you go down the periodic table, you end up with more and more shells, and so it gets bigger and bigger and bigger. That one makes sense. But as you go from left to right, why is it that as you gain more protons, that the size is getting smaller? Well, the reason for that is the nuclear strength of that element is getting stronger and stronger as it adds more and more protons. So it becomes a stronger magnet to pull in those electrons. So that size of that atom decreases. What we end up with overall is very small atoms in the top right-hand corner of the periodic table and very big atoms on the bottom left-hand corner of the periodic table. Okay, so our questions here are, why is it that the trend shows that atoms get smaller across a period? So that's from left to right. So what I said was, we had to discuss this in two ways. It's shielding and it's nuclear charge. So from left to right, shielding is constant because we're not changing the number of shells. They all have the same number of shells. What's different here is the strength of the nucleus is increasing because the nuclear charge is increasing. So those electrons are pulled in closer by the increase in the number of protons. Okay, second question, why is it that the trend shows that atoms get bigger down a group. And so that is because the number of shells increases, and so the strength of the nucleus is weakened by those shells with all the repulsions that are happening. It just makes the atom bigger. More shells, bigger atom. All right, now we're going to look at these three and determine which one would have a larger radius in these set below. So I need a periodic table. So if I find beryllium and barium on the periodic table, beryllium and barium are in the same column, so they're in the same group. And I know that as I go down, it gains more and more shells, so the bottom elements would be bigger because they have more shells, more shielding. And so we would say that barium is larger. Okay, between calcium and bromine. So calcium is in row 4, and so is bromine. We're looking across a period. And so calcium is on the left-hand side. And I know that as I go from left to right, the atomic radius decreases. I have my smaller elements over here on the right side of the periodic table. And the reason for that, so not only do you have to be able to predict which one is smaller, which one's bigger, you have to be able to explain the reasoning behind this. And so calcium has the same amount of shells, but bromine has more protons, so it has a stronger nuclear charge. So bromine would be smaller, which would make calcium the bigger one of those two. All right, lithium or fluorine. So lithium is over here in group 2, actually not group 2, period 2, and fluorine is in period 2. Fluorine is further to the right, which means it has more protons and the same amount of shells, and so fluorine would be smaller, and which makes lithium the bigger radius of those. Our next trend is an ionic radius. And before we can discuss the trend, we need to know what ionic radius is. And so that's just the size of the ion that's formed after it is either lost an electron or gained an electron. Here we have sodium turning into sodium 1+. So it goes from having 11 protons and 11 electrons to now 11 protons and 10 electrons. And so since now the nucleus is the same, but the number of electrons are different, that same amount of protons are better able to attract those 10 electrons. And so the size of the atom gets smaller. Another way to say that would be this. As an atom loses one or more electrons and becomes positive, it loses another energy layer, like a shell, and its radius gets smaller. So it looks like this. The electron is lost, turns into a lithium ion, and then you can compare the size of the lithium ion to the lithium atom, and they're very different. All right, what about the opposite direction when we're looking at chlorine atoms? And so chlorine atom versus the chlorine ion, chloride ion, you can see it's getting bigger. Here's why. Now it has more electrons than it has protons, and so those protons aren't as able to pull in those electrons as well. Another way to say that looks like this. As an atom gains one or more electrons, becomes negative, and it fills that valence energy level, therefore the size of the radius also increases. All right. In terms of the trend, elements in a group tend to form ions with the same charge, and this is modeled by their electron configurations. So, for example, everything in group 1A ends in S1. It has one electron, its last energy level, the s orbital. For example, potassium has this electron configuration, argon 4s1. And so it's easy for that potassium to lose that one extra electron in that outermost energy level in its valence shell. And so it does that, and it becomes just argon. It loses that extra layer or extra energy level. And it actually gains stability by doing this, by losing that extra electron to be like a noble gas, because those are the most stable things on the periodic table. And it wants a full set of electrons like a noble gas. And it becomes potassium with a 1+ charge when that happens. For negative ions, like oxygen tends to form a negative ion, here's its electron configuration. Helium 2s2, 2p4. And so it's really close to being just like neon. Neon's helium 2s2, 2p6. And so if it just gains 2 more electrons, it can be just like neon. And so it does. It wants a complete set, and so it becomes helium 2s2, 2p6. And when it does that, and it gains those 2 electrons, it becomes O with a -2 charge. Another trend that happens on the periodic table are charges. And these charges, we're just going to look at the group A representative elements. And so since everything in group 1A has 1 valence electron, it tends to lose that valence electron and become a +1 charge. Everything in group 2A, a +2 charge. It loses the 2 valence electrons. 3A, a +3 charge. 4A has 4 valence electrons. In order to be full, it would need 8. And so it can either lose those 4 and have an inner core like a noble gas before it, or it can gain them. And so we're just going to write ±4. And then in 5A, these just need 3 more valence electrons to be like the next noble gas. So when they do that, they become negatively charged. 6A, -2, 7A, -1, and then noble gases do not gain or lose electrons. They're very unreactive. So the overall trend is the elements on the left side of the periodic table tend to lose electrons, and the elements on the right side of the periodic table tend to gain electrons and become negatively charged. So here are the trends in ionic radius. From top to bottom, going down the group, as you add more energy levels, you increase the shielding. So from top to bottom, the size of the ions get bigger. However, when you go from left to right, overall, it goes from bigger ions to smaller ions, but it resets right in the middle. Why? Because the positive ones decrease in size. And then we have our negative ions, which start out a little bigger than our positive ions, and then they decrease in size. Looks like that. All right, so let's look at this bottom part of this table. As we go from left to right, from sodium to magnesium to aluminum, the size of the ionic radii are decreasing. And then there's a shift. It's all of a sudden gets bigger and decreases again. So it shifts between that part where these are positive ions and these are negative ions. Okay, and that ends part 1 of periodic trends. Next time we will discuss trends in electronegativity and ionization energy. So I'd like you to write on your periodic table that's in the back of your notebook right now. And